Okay, hello everyone. Now we're going to start a new topic in our course, and this is the thermal engines chapter. So this chapter is very important because we are going to state the second law of thermodynamics, and that's the last thing we need to complete, at least the basic foundations of the theory of thermodynamics, before we can apply it to actual systems of interest. And okay, so what we are going to do, as usual, I will walk you through the key points before starting. So we are going to see the second law of thermodynamics straight away in the beginning, and we are going to see that there are several equivalent statements of the same thing, and in particular we are going to look at Kelvin's, or Lord Kelvin's statement, and Clausius' statement of the second law. We will see that both are equivalent, although they seem to be very different. They mean the same thing, or they emerge from the same truth, which is the second law of thermodynamics. And then we are going to talk about different types of thermodynamic cycles, that is, cyclic processes in which there is an energy conversion process happening. So the typical example is a heat engine that takes a heat flow into mechanical work, but you can also think about refrigerators or heat pumps in actually other cycles as well. We are going to talk about how you quantify or assess the energy performance of each of these cycles, defining a suitable efficiency or figure of merit. Then we are going to introduce the concept of ideal thermodynamic cycle, and specifically heat engine cycle. And we will talk in detail about two paradigmatic examples. One is the Carnot cycle, and the other one is the ideal Otto cycle. So these two cycles are actually fundamentally different to one another. We are going to see why. And there's many others, of course, and we will just very briefly mention the Stirling cycle and the Ericsson cycle as other kind of Carnot type cycles. But I guess the key point, not only of this chapter, but possibly one of the key points of the whole course, is Carnot's theorem. So that's a really important result in physics, and we are going to see its statement and how you can prove it. This is not the way that Carnot proved it, but it's a simple way to prove it. Because we will prove the theorem, we are going to be able to see the consequences. So we specifically will know exactly what the consequences of Carnot's theorem are. And one of the most important consequences is that we will be able to finally establish thermodynamic or true thermodynamic temperature scale. Because remember that up to now we had simply agreed to take a gas thermometer with an ideal gas at constant volume and measure temperature in the Kelvin scale, and we just took that to be equivalent to the true thermodynamic temperature of a system. Now we are going to see why this is the case. Okay, so we'll just begin by stating second law of thermodynamics in different ways, and the first way, I already wrote it beforehand, not to waste time, is Lord Kelvin's statement of the second law. So let's just read it, and then we will try to process what it says. So no process is possible whose sole result is the extraction of heat from a single reservoir and the performance of an equivalent amount of work. Okay, so let's see what it says and take it in. So I guess first thing, reservoir. Reservoir is the same thing as a heat source that we have defined properly. So it's a system that can exchange heat with you without changing its temperature. And then it speaks about absorbing some heat and performing an equivalent amount of work. So remember this, the fact that back in the day, the notion of energy was actually not well established. Now it's very natural for us to speak about energy, but back in the day people didn't know what energy was. And so remember, heat in the beginning was measured in some new heat units, the calorie. And with this experiment of Joule, among others, it was established that there is a mechanical equivalent of heat. So actually calories can be transformed into joules, and they can be measured in the same units as work. But you see here in this statement, people were still talking as though heat and work were not really the same thing, but you can kind of transform one thing into the other somehow. Now for us it's very intuitive that they're both energy, they're both ways of exchanging energy. So they are really equivalent to internal energy. So this equivalent amount of work, we could forget about it and just say you absorb some heat and then release it as work. Okay? So what it says, once again, is that you cannot take a thermodynamic system and invent some kind of smart process in which could be equilibrium or non-equilibrium, it doesn't matter. But the result of this process, once you are done with it, you finished, is that you took some heat out of a heat source, and then you perform all of that heat, you transform it into mechanical work that you make in the environment. So it's negative for you. This is another key word here is sole. So the sole result of the process must be that. So it means in particular that your system must start in an equilibrium state and finish in the same equilibrium state, so that nothing changes in the system. The only thing that has changed is that some heat has been absorbed and the same amount of work has been performed onto the environment. But the system must be in the same state in which it started. Okay, so whenever you have a thermodynamic process that goes in a loop like that, in a cycle, we saw that in previous chapters, you talk about the thermodynamic cycle as well. Okay, so that's what we mean. It's simply a process where you start and finish in the same state, and the process does not need to be quasi-static. It can be arbitrarily non-equilibrium if you want. So okay, that's a thermodynamic cycle, and if a thermodynamic cycle produces work, so that it means the work is negative, meaning that some work is made on the environment by the system, then you call it a heat engine cycle. Okay, so just knowing the definition of a heat engine, we can rephrase this kind of old-fashioned language into something a little bit easier to understand. This is my version of the Planck-Kelvin or the Kelvin-Planck or the heat engine statement of the second law of thermodynamics. And it says that it is impossible to devise a cyclically operating device, the sole effect of which is to absorb energy in the form of heat from a single thermal reservoir and to deliver it as work. Okay? So you see that this is slightly more modern because it uses the word energy, and it divides energy into forms, form of heat and form of work. And then it makes it very clear that you are talking about a cyclically operating device. So you're talking about a process that starts and ends in the same state. The system starts and ends in the same state. So then there is the other statement that I wanted to introduce, which is Clausius' statement. It looks really different. So actually, let me just make it clear, this Planck-Kelvin statement is really equivalent to Lord Kelvin's statement. It's the same thing directly. We don't have to prove its equivalence, just rewording of the same thing. But this one here seems very different. And if we want to say that this is equivalent to Lord Kelvin's statement, we have to prove it somehow. So it says, no process is possible whose sole result is the removal of heat from a reservoir at one temperature and the absorption of an equal quantity of heat by a reservoir at a higher temperature. Okay, so let's again take in what it says in here. Again, there is this sole result, so we are talking about the cyclic process, and this cyclic process, what it's doing is to take heat from a reservoir at some temperature and to take all of that heat into a reservoir at a larger temperature. Now remember that when we introduced empirical temperature scales, we said that meaningful temperature scale is such that it assigns a higher temperature to those bodies from which heat flows naturally into others, right? So if you have two systems, A and B, and you see that system A will give out some heat to system B naturally and spontaneously, then any decent temperature scale should tell you that system A is at a larger temperature than system B. Okay, So what this is saying is that you cannot make a cyclic process in which a thermodynamic system makes heat flow uphill, like against its natural tendency to go from lower temperature to higher temperature instead of going from higher temperature to lower temperature. Okay. So what we have to do now is to prove that these two statements are equivalent.